We shall next focus on binary relations, and relations are also discrete structures. We first focus on set, then we move on to cross products, subsequently to relations. If A be the set, A could be a finite set or an infinite set, we talk about cross product, either A cross A, or if it is two sets then A cross B. If it is three sets then we talk about A cross B cross C and so on. If the set A has got say so many elements, A1, A2, so on up to AK, then A cross A is also a set consisting of AI, AJ, such that AI, AJ belongs to A. If the sets are different, say A consisting of A1 to AK and B consisting of B1 to BL, then A cross B is a set containing the pairs AI, BJ, such that AI belongs to A and BJ belongs to B. And essentially A cross B contains all possible pairs. So now you can see that the cardinality of A cross B is each one you perform cross product with each element here, which means it is KL. Okay, and if you work with just one set, then cardinality of A cross A is K into K, which is K square. We define another set called a relation denoted using the symbol R, which is a subset of A cross A. Since it is a subset of A cross A, this R we refer to as a binary relation. For example, A consisting of say 1, 2, 3, then A cross A has so many pairs, say 1, 1, 2, 2, 3, 3, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2. Okay, and this one is redundant. So you see that this has got 9 elements, and relation R1 is a subset of A cross A. This could be maybe 1, 1 and 3, 1. R2 is a binary relation. R2 may be 3, 3 alone, and R3 could be an empty set. R4 may be A cross A. So there are many subsets, and each subset of A cross A is a binary relation according to our definition. So given a set which is a discrete structure, and because we work with discrete sets, the next discrete structure with respect to discrete set is cross product, which is also a set, and set consisting of elements, whereas cross products consisting of pairs. Now we define another set which is a subset of A cross A or a cross product, which is called a binary relation. So just like there is a cardinality associated with A cross A or A cross B, one can talk about how many different relations are possible, how many different binary relations are possible. And this can be generalized. If the cross product is A cross A, then you get to see that it is not pairs, it is tuples of size 3. So AI, AJ and AK, where AI, AJ, AK comes from this. Now if a relation is a subset of A cross this, then R is referred to as a ternary relation or a three-ary relation. So in general, we talk about A1 cross A2, so on up to AK, and if R is a subset of that, then R is known as k-ary relation. If it is 2, then it is binary, and if it is 3, it is ternary. If it is k, it is k-ary. Now the interesting part is, are there unary relations? Answer is yes. If you have 2, then it is binary. If it is just 1, then it is unary. What is that? Any subset of A is a unary relation. That's it. Any subset of A is an example unary relation. Now, having given the framework for relations, let's get into some interesting counting. If A has got n elements, then we know that A cross A has got n square elements, and R is a subset of this. So the question is, how many different binary relations are possible on A? So answering this is equivalent to answering the number of subsets on A cross A, because each subset is a binary relation. So counting this is equivalent to counting this. So if A has got n elements, then number of subsets is 2 power n. Correct? This is also known as cardinality of this, the size of the power set. A simple argument for this is, so there are n elements, A1, A2, so on up to An. We either include this or exclude, include or exclude, include or exclude. Supposing we include this, then we get the subset, all of them. We get the subset A1 to An. Suppose we include these two, rest of them we exclude, then we get A1, A2. Suppose we include A3 and A7, rest of them is 0, we get this. And we include none, which means we get empty set. So something like this. So if this is 1, 1, 1, we get this. If this one is 1, rest all 0, we get this. If all of them are 0, we get this. This tells you something. Number of subsets on a subsets on a set of size n is equivalent to counting number of binary strings of length n. So this is a binary string, this is a binary string, this one is a binary string, this one is a binary string. How many different binary strings are possible? And each binary string corresponds to a subset. Equivalently, from a subset you can generate an equivalent binary string. Now each element has two possibilities, 1, 0, 1, 0, 1, 0. So in some sense it is 2 into 2 into 2 n times. Therefore the number of subsets on a set of size n is 2 power n, or number of binary strings of length n is 2 power n. Put it in other words, if the size of the set is n, then number of subsets is 2 power n. What is that we want? Number of subsets on A cross A. Since cardinality of A cross A is n square, number of subsets on A cross A is 2 power n square. So number of different binary relations is 2 power n square if the cardinality of the underlying set is n. So this tells you that there are exponential number of binary relations on a given set, on a given finite set of size n. Okay. One can list all of them. And for example, if A happens to be 1, 2, and we know that A cross A is 4 and number of binary relations is 16. So the first relation is empty and second relation is 1, 1, third relation is 2, 2, and fourth relation is 1, 1 and 1, 2, and fifth relation is 1, 2, 2, 1. So like this one can list. Finally we get R16, that would be A cross A itself. So you find 4 elements, 1, 1, 2, 2, 1, 2, 2, 1. Then you look at all possibilities. So we see that there are 16 of them. Now what we will do, we shall describe some properties on these binary relations. And now given a binary relation, we will ask, does the given binary relation satisfy so and so property or not?